Hello, and welcome to this lesson on the intermediate value theorem. This is found in the end of the limits unit in calculus, and it's also found in a unit in pre-calculus. So this is an idea that is obvious once you start talking about it, but it becomes very important. It is what allows us to know that a zero of a function will be guaranteed in an interval that is, if one side of that interval has a function value that is negative and the other is positive, or vice versa. So let's just take a look at this for a minute. So if a function is continuous, so the intermediate value theorem only applies to functions that are continuous, and we've spent some time looking at that in calculus for sure. It means you can draw it without picking your pencil or pen off the paper. If it's continuous on a closed interval, a to b. So let me just I'm going to say this is a, I'm going to do this kind of randomly here, and this is b. It takes on every value between f of a and f of b. Now, f of a will be whatever height this is. So it's the function value. So this is f of a right up here. I'm going to draw a function in a minute. And f of b, well, f of b can be anywhere. I'll put it down here. The height at which that curve ends. Now I've got to draw a curve here. This is f of b, the height there, so that y value. So I can go up here and down there. Now this theorem doesn't say anything about any of the how far up or down it goes. Let's say f of b is 1, 2, 3, 4, 5, 6. That looks like a -6. And f of a is 1, 2, 3, 4. If I've miscounted, just pretend I counted right. So what this says is that there will be y equals every number between, and this is every real number, not just every integer, -6 and 4 somewhere on this graph. Between x equals a and x equals b. Now notice it doesn't say anything. I could have drawn any function that was continuous, and this would be true. I could have drawn a line. I could have drawn something even crazier than I drew. It has nothing to do with the fact that this goes below -6 or above 4. All it's saying is that every y, and let me change colors here, between the y is 4 and the y is -6. Every y represented on the y-axis by this red line between that function value and that function value will exist on this graph. So if you look at this, well, if you say, well, y is 0, oh yeah, okay, I go over there, this is 0. If y is, you can see that for every y coordinate, I can find a point on the graph. It has to pass through all of them. To get from here to here, I must pass through all of the y values in between. And you say, well, so what? That's kind of obvious. And, well, so what is this? Now, in this particular case here, I can see that f of a is positive. Now, when positive means greater than 0, when I see greater than 0 written down, I say to myself is positive, because this positive is really what has meaning to me. F of b is negative. The signs are different. In between any positive than negative, if you go from positive to negative, or if it had been the other way around, negative to positive, you are guaranteed to have had to pass through 0. Your number line goes like this. Here's 0. It is the dividing line between negative and positive. Anytime you start on one side of the line and want to go to the other, you have to pass through 0. So this is the big important point of the intermediate value theorem. If you can find an a and a b at which the y values are different on that function, you know there's guaranteed somewhere between that a and b, and in this case there's one right about there. It's like 1.2 or something. between a and b somewhere, there is a zero of that function. Zeros of functions become really important. When you take circuit design classes, you learn that zeros of functions are what create smoke in your circuits. You don't want things to blow up. You get all sorts of crazy things happening if your zero is in the bottom of a function. So, and there's other reasons to know zeros of functions. We're going to use this a lot in this class. But what the intermediate value theorem says is you're guaranteed to find a zero in an interval if you know at one end of the interval your function had one sign, and at the other end of the interval in x, your function had the other sign. You know somewhere it had to cross through a zero. And this is used to find zero sometimes, and there's some sophisticated sum and difference quotient methods and things. Your calculator can find zeros. If you use a graphing calculator into the function that says calculate zero, it insists that you find one value that is positive and one value that is negative. So if you were looking for this zero here, you didn't know exactly where it was, and you wanted it like within 3 decimal places, you'd have to move a line so it picked the function like over here. You have to actually outline a boundary on each side such that on one side you pass through a positive value, and on the other side your boundary passes through a negative value. If I were to pick 2 on the same side and not actually catch the zero for some reason, or if this came back up and I picked 2 positive ones, I would get error sign change. Because if the signs are the same, it doesn't mean there isn't a zero, but you can't guarantee there is one. If the signs are different, you guarantee that interval has a zero in it. And then you can start making that interval smaller and smaller. And I'm pretty sure I had to write some code at some point in my life, in some sort of a class, whether a math class or an engineering, that bisected this until you found something that was close enough to zero that you said, oh, I found the x value that creates the function value of zero. But this intermediate value theorem, all you have to know is it guarantees it to exist. So what do your questions look like? Well, here's what a typical question would look like. And I'm going to erase this, so there's fair warning. Stop the video if you want to copy this down. So I'm going to clear my canvas here. Oh, I've cleared the whole thing. Let me see if I can recover my... Oh, there we go. There's my problem again. Sorry, I realized I didn't snap that to the background. So the bottom problem here. Use the intermediate value theorem to show that f of x equals x squared plus 2x minus 1 has a zero. So this is our a and this is our b. So find f of a. Not the hardest thing we've done. F of 0 is 0 cubed plus 2 times 0 minus 1, and that equals negative 1. F of 1 is 1 cubed. Make sure your arithmetic is good. Many of us are having arithmetic issues, not calculus issues. So I get a 1 minus a 1 plus a 2. I get a 2. Oh, look, this is negative, and this is positive. That means somewhere between 0 and 1, this function, x cubed plus 2x minus 1, has a function value that's equal to 0. That means it's worth looking for in that interval if I were looking to find the zeros. We've lost some of the utility of this and the fact that we have all sorts of graphing calculator stuff to help us find zeros, but it is still a useful theorem, and it's kind of just a cool thing that, oh yeah, that's the way it always works. Okay, so that's all I have for this intermediate value theorem lesson, and email me your questions. Thank you.